Good afternoon or good morning, depending on where you are. I'm Professor Prof Orata. We are continuing with our lectures in thermodynamics. Then we want to look at measurement of how can we measure empirically, how can we measure internal energy, and of course by extension internal energy and enthalpy measurements. We have already talked about the flow calorimeter in other lectures, so we'll focus more on measurement of internal energy and see how we can relate that to determination of the heat capacities, isobaric and isochoric heat capacities. So let us look at the measurement of internal energy, U. Cp and Cv. Now, we have already seen that from first law of thermodynamics, using the non-flow expression, that is du is equals to dq plus dw, we saw that under constant volume, then that expression for first law, which is du is equals to dq minus pdv. Remember, we are talking of PV work only, and there's no non-PV work. And always remember that when we are talking of PV work, but there are other forms of work. There's electrical work, which when you look at the flow calorimeter lecture, you will see that we talked of electric resistance, where that's the friction in the electrical flow system, and which leads to loss of heat from the electrical context. Just like in the friction in the mechanical context is conversion, results to loss of mechanical energy as heat. And so we are saying that it is very important for us to know that there are other forms of work. This could be electrical work, tension work, so many things. There are many other forms of work. So always don't act like as though it is only PV work. There are other forms of work, only that those forms of work are not important to us in our discussion at that particular point in time. Like I said, when you go to the flow calorimeter measurement, empirical determination of enthalpy, you'll see that electrical energy now is important. Now, so we are saying that du is equals to dq minus pdv. So if the volume is constant volume, that is delta V is equals to 0, therefore this quantity will be 0. The quantity will be 0. So that du is equals to dq under constant volume. Now, so what does that mean? That means that we can have a constant volume system. We can have our constant volume to determine internal energy. We have a constant volume system. Remember, in bomb calorimetry, we had a constant volume bomb, which was a unit there, where we were able to measure heat being transferred under constant volume. So we have a unit where we can measure heat being transferred under constant volume. Now, suppose, for example, so we are saying that the volume, so we are talking of a system where we have constant volume. We have constant volume and we measure heat transferred. So that if you have, for example, you have your constant volume remains at VI, and then the pressure corresponding to that is P1, then we generate another coordinate, and the same constant volume, and of course different temperatures, I, there will be pressure 2, another one, VI, pressure 3. So we measure these changes of heat quantities versus temperature. So we determine heat produced at different temperatures. So if you have that, your constant bomb unit. If you have your constant volume bomb, and you keep determining the amount, so there's a constant volume bomb. You continue computing the amount of heat produced at different temperatures. Then you are going to generate a table of U versus temperature. So you generate the values U versus temperature. T1, U2, T2, and so forth, UN, Tn. Keyword, keep catch here. This is heat transferred under constant volume, and that value gives you the internal energy. So you measure these quantities at different temperatures, and then you plot that curve, that graph. You plot the graph for U versus temperature. You plot the graph for U versus temperature. And so whatever you get, U versus temperature from this particular system, also compute the slopes. You compute the slopes, U. How the U changes with temperature under constant volume. How U changes with temperature under constant volume. So you have obtained your values for U versus temperature. Compute how that internal energy varies with temperature from the slopes which you will obtain for U versus temperature. U at temperature 1, U at versus at temperature 2, how it varies with temperature. So you get that slope under constant volume, remember, under constant volume. And so you have the different values at different temperatures. You'll have the different values at different temperatures, so forth and so forth. So from your plots of U versus temperature, you are going to get the slopes. You are going to get your slopes, and the slope represent the heat capacity at the different temperatures. So that when you now plot variation of heat capacity with temperature, you will end up with the type of plot. So on plotting variation of heat capacity, that is CV, this is normally in kilojoules per Kelvin per mole, versus temperature, you will obtain different curves, plots. You'll obtain those kind of plots. That's not drawn to scale, but the shape is in generally correct. So CV versus temperature, that's what you get. That is when you measure the heat transfer in a constant volume, you will get your internal energy values at different temperatures. Then you get the slopes of those internal energy versus temperature plots to give you how internal energy varies with temperature under constant volume. Remember, under constant volume. And then when you now plot those values for heat capacity under constant volume, you'll obtain this kind of plots. It will give you heat capacity versus temperature. And of course, in the same way, when you get your heat transferred under constant pressure, which we have discussed already extensively in the flow calorimeter in one of the lectures where we determine empirically the enthalpy, you will also have for CP, that is how enthalpy varies with temperature under constant pressure. You remember that you will have this enthalpy, that is DH is equals to heat transferred under constant pressure. Under constant pressure, you will check that in the flow calorimeter lectures, where we have shown how to measure empirically the enthalpy. So once you make those enthalpy measurements, in the same way, you take their variation with temperature, and of course the slope, which is on a constant pressure, will give you Cp, which is the isobaric heat capacity, again is in kilojoules per Kelvin per mole. And then in terms versus temperature, you will get kind of a U-curve. So you will get that kind of a curve. But remember, you have to be careful. You have to work in the single phase region. Because why are we saying that? Remember, we say that when we have phase transition, when, for example, we have phase transition, let's take again carbon dioxide, solid, liquid, gas, we say that where the two phases coexist in equilibria, their chemical potential are the same, and in those phase transitions, solid to liquid, that is fusion or melting, the temperature is constant. And for example, when you have liquid going to gas, that's vaporization. Again, at that point, the two chemical potentials are the same for liquid and gas. For their components, the particular components are the same in liquid and in gas. And at the same time, during that transition, the temperature is kept constant. That is during vaporization, the temperature is kept constant. So why do you want to work in the single phase region? Because if you delve into the region where there's phase transition, then it means that if you're talking of Cp, which is basically delta H over delta T, or you're talking of Cv, which is delta U over delta T, then these quantities will be zero. And so if they are zero, then you see that those will be infinite values. And you don't want that. You don't want that. So you want to confine yourself to the single phase region. Just in summary, I repeat, we can determine these quantities empirically. We can measure the enthalpy. We can measure the internal energy. And the key anchor there is the simple fact that heat transferred under constant pressure is the change in enthalpy. And that is the basis with which we develop the flow calorimeter in those lectures there. And now we are saying the heat transferred under constant volume is the change in internal energy. So you measure, you determine the change in internal energy from the measurement of the heat supplied under constant volume. So you determine the internal energy values at different temperatures, you plot that to get the slope, and then that now gives you the change in internal energy with temperature, which is Cv. And then now when you plot this Cv versus temperature, then you get the kind of plots which you have for internal energy, and also you get the kind of plots which you have for enthalpy. So let's stop at that point. We'll pick up with other lectures subsequently. Thank you.